Here we go. So let's talk about Azure Cosmos DB. This is why, at least I'm in this room. Hopefully you guys have found the right room as well. My name is Andrew Liu. I work on the Azure Cosmos DB engineering team as a PM. And today we're going to talk a little bit about what is this thing, why do you care, some of the use cases and case studies, as well as we're going to take a look at how you can take advantage of this. So I guess, how many of you guys have heard of Cosmos DB before? Awesome. And how many of you guys have played with it? Cool. And so by the end of this, you're gonna really want to raise your hand if you didn't. But so in a nutshell, like what is Azure Cosmos DB? Just for a very, very quick summary for those of you guys who haven't seen it, it's a globally distributed, massively scalable, multi-model database service. And the way I like to think about this is actually, what we do is we start with the core underlying platform. And so the core underlying platform is we build a massively distributed system. And what it offers is turnkey global distribution, elastic scale of throughput, storage and throughput, guaranteed low latency, a tunable consistency model, and it's fully managed with comprehensive SLAs where we actually guarantee characteristics around high availability, throughput, latency, and consistency. And so, in a nutshell, what this means is we're basically good at two things very strongly from a technical standpoint. Very, very strong in terms of replication, very, very strong in terms of partitioning. And this basically solves a category of problems that people like to think of in terms of basically scale and performance. In order to scale, basically you need to be able to scale out, right? And this is where partitioning comes into. If you ever get to a point where a single machine is a bottleneck, the concept of scale up is buy a bigger machine. The problem with buying a bigger machine is there's a ceiling. Once you have the biggest, baddest hardware, you go, oh, what do I do now? Solution simple. Get 2 machines, get 3 machines, get 1,000 machines. And so this is the concept of scale out. And over the years, really where databases has gone is rather than having you scale across many, many instances and people giving you tooling to do so, what if we built a database platform that natively scaled out behind the scenes so that you actually just give a hint on how do you want to distribute the data, database takes care of the rest. The other thing that the platform, really what it really boils down to is replication. And replication can be done for several things. Number one, most people think of is availability, right? It gives you a high amount of redundancy. So if you have mission critical application, you cannot afford downtime. What replication allows you to do is if one copy goes bad, doesn't matter. You have many other copies to fall back on. However, now replication can actually be used to extend well beyond availability. And so what we do with turnkey global distribution is actually we can actually ship data closer to where users are. Rather than just replicating within data center, we can actually replicate basically all around the world and give you a ubiquitous presence. And this gives you an ability to solve this annoying problem called the speed of light problem. The speed of light problem is if I have users, let's say all around the world, I have some friends back in Seattle where I am from. If I have my database based here, sending a packet from here to Seattle is going to be a couple hundred milliseconds round trip. Now if I need to do several round trip, this becomes, well, my application is very, very slow. And I really can't send a packet faster than the speed of light, but what I can do is I can say, I'll cheat it. I'll just bring the data very, very close to where my friends are all around the world. And really this becomes, you actually then go into the next problem, which is the consistency problem. If I write data in one region and I read it in another region, what is that behavior? Does it actually wait for this data to propagate, or does it actually serve data very, very quickly? And so I actually will, by the end of the talk, you're going to be experts on all of these concepts as I delve in deep into these. But this is the underlying platform, and on top of this, what we do is we actually we have our own way of representing data underneath. We call this ARS, Atom Record Sequence. But in a nutshell, what that means is we actually build a tree representation of the data underneath where the schema is self-describing, and it gives us some very, very neat characteristics. Number one is it allows us to ingest data without having to define the schema up front. Now that's going to be very, very important when you're dealing with problems at scale, because as you know, if I have a massively partitioned database replicated into several regions, things like alter tables, create index become, well, a deployment mess. Number two, it allows me to do automatic indexing of data. I'll talk a little bit about how indexing works behind the scenes. And number three, what's really interesting is you can actually project many different data models natively on top of this. And so the data models that we support include key value, column family, document, and graph data models. And so this is kind of a layer on top of the core platform. And what we do is we actually expose a set of APIs for the corresponding data models, including a document DB, SQL, and JavaScript API, a Gremlin Graph API, a Tables API, and a MongoDB API. So this is kind of in a nutshell what we're about. And I'll tell you a little about our story as well. So we started this project in 2010 called Project Florence. And basically, we saw a need for this kind of system internally within Microsoft. Our very, very first customer was actually the OneNote team over in Office. And they basically needed a database that handled these characteristics. Basically, elastically scaled to handle a very, very massive user base. The number of Microsoft users tends to actually be quite high. Be able to actually serve users all around the globe with very, very low latency, and also have the schema agnostic property. But over time, what we found was within Microsoft, this became increasingly popular. We saw this adopted by Skype team, by Xbox, by Universal Store within Windows, by even our across many Azure services, including the Azure Portal and the Azure IoT Hub, is all built on top of Cosmos DB. And so what we found was, you know what, this is not just a unique need for OneNote. We at Microsoft needed this, and then over time, our customers were also asking, like, "Hey, we're finding common patterns. Where do we, how do we actually expose this?" So in 2014, we released Document DB, where we announced the first set of capabilities out to the wild, and then earlier this year at Build, we basically released all of our features out into the wild as Cosmos DB, and today this is the fastest growing service in Azure. And so to kind of show you the momentum, where if you go to DB Engine rankings today, we're already the #2 graph database on the market, and we released our graph API just half a year ago. So we took the world by storm, and really, like, hopefully by the end of the session, this database will actually be kind of demystified for you. Chances are, if you weren't using Cosmos DB directly, you're already using it today, just indirectly. We have over 6,000 happy paying customers already implementing production solutions on top of Cosmos DB. Chances are you are using Cosmos DB, whether you know it or not. So let's talk a little bit about some of the patterns we see. Like, given this breadth of adoption for Cosmos DB, what are people actually building and why? So if we were to actually take a look at all of our top use cases and kind of get an understanding of what are people doing, we can actually categorize all of our users. In one bucket, we actually see lots of adoption in IoT. And really, the reason why is because IoT has a set of challenges that include scalability, and this is going to be both the amount of data as well as throughput. If you think about devices and storing device telemetry, machines produce data at a phenomenal rate, much faster than typically humans can. So, I mean, I tweet every now and then. Maybe I'll tweet, once or twice a day. But a machine will actually generate data points and say, "Hey, here's my state. 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 Here's my state," and keep pounding you, telling you basically what is the state of the system. And now, if you deploy, let's say, 1 million machines, let's say you're Toyota, where you have every year you're selling millions of vehicles. Each of these are actually recording the states. You now have basically a need to be able to support millions of writes per second. And on top of this, it's all good that you can absorb this data. However, you want to produce value out of this, right? And so example of what Toyota is doing today is the moment you get in a car accident, if you actually use their Service Connect service, what it'll do is it'll say, "Hey, airbag got deployed. Maybe we should call the driver and see if he's okay. And if he doesn't pick up, maybe we should call emergency services and say, we had a driver, airbag got deployed. I'm having trouble reaching him. Can you go on site and make sure he's okay?" And in order to do this, basically you now need a database that not only absorbs data at an incredibly fast pace, but needs to be able to serve the data back out with very, very low latency so that you can really build and bring a lot of value back to your end users. On top of this, one of the other challenges is devices are really difficult to update relative to software. Like for a software service, you hit update, and really you can just push another service update on. If it's box software, maybe you also need to support several different versions in terms of how you upgrade. However, at the end of the day, like, it's a solvable problem. For machines, it's a little bit more difficult because what happens is over time, each generation of machine is going to have different sensors. It's going to have different things that you keep adding on over time. And it's very, very hard to actually go back and retroactively make sure that all of your devices deployed out there have the exact same hardware. And as a result, the telemetry is going to look very, very different based off of the generation of hardware. And so what ends up happening is you need a database that is able to actually support this heterogeneous data, where every record coming in might actually look a little bit different. And so let's take a look at some of the patterns that they use. Typically, there's many ways of implementing such a solution, but this is one that we found was really quite common, is you use something like IoT Hub first to establish a bidirectional way of communicating with the device. That way, not only are you able to absorb events coming in, but you also are able to do things like push commands back down. So an example is refrigeration, right? It's good to know that maybe temperature is rising for your refrigerators for a batch of goods, but it's even better to be able to react and say, hey, I don't want those goods to spoil if I see temperature going up. I want to actually send command back down to basically kick in some backup refrigeration unit and make sure that the goods don't spoil. As those events come in, all this telemetry comes in. One option is to actually use a stream processor. We have a few stream processors ranging from Azure Stream Analytics, as well as Storm and Spark on Azure HD Insight. And what this will do is you can actually also build some logic on the stream side. Stream side can also do things like pre-aggregation. And so typically what we see a lot of people do is they implement a Lambda architecture. And in this Lambda architecture, you might actually be putting pre-aggregates in SQL to power a Power BI dashboard. However, once you see an anomaly on that dashboard, having just a pre-aggregate is not enough. It'll tell you that maybe something is off, but you want to actually debug the system. And so this is where Azure Cosmos DB comes in, is in order to actually ingest all of these raw events coming in, you need that database that can absorb all of these writes per second. And so Cosmos DB is typically used as a hot store in this scenario. We've also seen patterns where people will use other code stores like Azure Data Lake or Blob Store for archival. But basically, where Cosmos DB fits in the Lambda architecture is it is your de facto go-to hot store. Off of this, we also have some neat functionality like a change feed. Basically, one of the techniques we use for absorbing very, very high rate of write ingestion is it's a log append store. And I'll talk a little bit about change feed later in this presentation. But because we have a log append store, we can actually surface the log back to you and basically use this as a mechanism for also surfacing incremental reads from the database, which you can then drive events and build event-driven architectures on top of. And speaking of that, if we look at some of the other very, very common use cases for Cosmos DB, we actually see Cosmos DB used in the retail industry quite pervasively, from running our own universal store to Jet.com, which was recently acquired by Walmart, to even companies like Domino's Pizza for doing their ordering pipeline for all of their franchises, and so forth. But really, a lot of the challenges here are you have very, very seasonal workloads. For e-commerce, Black Friday actually is going to be your peak season where you get 10x the traffic that you typically get for the rest of the year. And in order to scale a database for that, you don't want to actually pay for peak cost, a large, massive cluster all year round when only you need it about 1/4 out of a year. And so really you want elasticity. You want the ability to scale up during things like Black Friday, Cyber Monday, last through Christmas, and be able to scale back down. And as more and more stores are going from the old brick and mortar model over to e-commerce, so an example is one of our other customers, ASOS. They deliver to 200 countries worldwide. in order to actually serve customers from 200 different countries, what they need to do is actually have a very fast, robust web experience for all of their users. And this means that shipping data closer to their user allows them to actually build very, very fast web experiences. And really a lot of the other needs here are, things like product catalogs. Not every product actually looks the same. If I have a store where I sell, let's say, this bottle of water, I might actually tell you that the bottle itself is recyclable. It's eco-friendly. However, if I were to add this eco-friendly, recyclable product attribute to all of my products, let's say to this mobile phone, I'm going to be very confused and why when I query for is recyclable, a mobile phone comes up. Instead, I might actually want to look for, let's say, the radios on here, like if it has a Bluetooth radio or NFC. But then when you even think about products in that dimension, even for a single product type, not every mobile phone is the same. If I have a Motorola Razr versus a new smartphone, older phones don't have some of these new radios. And so basically every one of these records is going to have a different schema again. So within retail, we actually see several different areas that are commonly reoccurring. One is in product catalogs, just because of the heterogeneous nature of each of these different products. But some of the more interesting use cases are around order processing pipelines. And what we're seeing increasingly is people actually break out their order processing pipeline into a set of microservices. They'll have a microservice that when an order event comes in, what I'll do is that I'll start doing tax calculation, generating, is this sales tax, is this VAT tax, and let me generate an audit record for bookkeeping. Once that calculation is done, another microservice will kick in and actually charge the order for payment. And then this will actually lead on and on until you have microservices that actually go out and take, an order that has been processed for payment to actually start boxing it up and shipping it out to the user and generating a shipping notification. Now, when you build such an event-driven way of communicating across all of these different microservices, if one of the needs here is basically reliability. What if a microservice crashes, right? Basically you're looking for some way of storing events to broker the events between microservices and ease communication. That way you don't have n microservices talking to n-1 other microservices. However, you have a need here where if one, let's say, service crashes, let's say the payment microservice crashes, you want to be able to actually go back and replay those events to make sure that you don't have orders that are just kind of lost and stuck in limbo. And so this is where Cosmos DB comes in, is using the change feed, you basically have a persistent event store. All of the events are going to actually be written to disk and persisted. And so that way you can actually build highly resilient event-driven architectures, go back in time and replay those events. And so if you want to also then build things like BI dashboards on top of this and materialize a set of views, you can actually go back in time and retroactively change what your materialized views by rebuilding them and playing events back in time. Another area we see a lot of usage is in real-time recommendations. And typically how these are built is also using kind of there's a Lambda architecture way of design pattern. And what we see a lot of people do is basically for the online recommendation, when a user comes in to a product landing page, you right away want to actually go and understand who is this user? What is their browsing behavior? And that way we can actually recommend an intelligent set of products. For example, if I am purchasing a mouse, maybe you also want to show me things like keyboards as opposed to showing things like water bottles. It'll be a lot more relevant to the end user. But here's one of the challenges is in order for you to actually personalize that recommendation, you have a very, very strict amount of latency you can tolerate before you render that page. That page still needs to be able to load fast. And that's one of the big differences between a real-time recommendation system and a non-real-time recommendation system. If you're doing something like just mail marketing, it's okay if your calculations take, let's say, an hour to complete. But for loading a real live website, this needs to be very, very fast. And so the way you actually build such a system is you're basically going to have an online recommendation service. And what it'll do is two things will happen. Let's talk about the hot path and the cold path, maybe starting with the cold path to kind of give you a whole end-to-end view of how something like this is actually built. As user browses events, purchases products, all of these events are actually going to go to an offline recommendation engine. And with this, you're actually going to build a machine learning model. You're basically going to calculate two things. One is a vector for each individual product. Another is a vector for each individual user. And if you take the dot product of these two vectors, the calculation you want is the probability that they will actually buy, that user will buy that product. And what you're going to do is, once you have calculated these two vectors, you're going to pump this into your hot store, into Azure Cosmos DB, so that way, when user now browses the website and needs to hit the recommendation service, you can actually host that a decision engine online. In this case, ASOS used Service Fabric to perform just the mathematical calculation. But that will need to be able to basically reach into the database and get, in less than 10 milliseconds, both the user profile as well as the feature vector for a particular set of products. And this way, the end-to-end latency for generating this recommendation, you have very, very fast load times. You can do this in milliseconds. A few areas that are also kind of interesting that we've noticed is in gaming. Gaming is kind of an interesting industry in that their traffic is very, very different from most other industries. In most industries, like in retail, what you'll see is peaks that are highly predictable around Black Friday or Cyber Monday. Or if you're building a database as a service, what you'll see is the number of users and the number of requests per second actually goes up over time. But how many guys, by the way, play games? Do we have any gamers in this audience? So you all know, like from a gaming perspective, like you like to play what's new. Like a lot of us like to play 5-year-old video games or 10-year-old video games, and so what ends up happening is on day one, when you see this new video game come out, you go, oh, maybe I want it. And you know, if you've ever bought in a video game and on day one, the online service, the social multiplier features don't really scale, you're really bummed out. And for a few of us, you'll get so bummed out that you might go to the Steam store, you might go to Metacritic and actually write a negative review saying, you know what, this multiplayer experience is not what I wanted. And if the reviews tank on a game, it becomes a very, very heartbreaking story for developers, because you basically spent the last 2 years building this awesome video game, and then on day one, just because you weren't able to scale, like all the reviews are now terrible and no one will actually go and play your video game. And so basically you now need to be able to scale on day one without really knowing ahead of time how many users are going to come in. This is actually one of the biggest reasons why more and more gaming services are adopting both cloud technologies like Azure as well as things like Cosmos DB. Furthermore, if you've ever played a game, a multiplayer game where the ping is high, you know that, I mean, latency is critical here. If you have, let's say, 100 millisecond ping or higher, you're going, man, this game is, this multiplayer experience is not very good. And so whenever you're doing things, let's say, driving the multiplayer experience, you need the end-to-end latency to be very, very low. And so this is actually one of the other reasons why even internally within Microsoft, as we build our games like Halo 5 and Gears of War, the multiplayer experience, we choose Cosmos DB. And Azure gives you a really nice actually set of tools, both from the Azure CDN, in which static assets can be served very, very quickly to users, as well as Cosmos DB for the dynamic content for all of the social and multiplayer gameplay. On top of this, we have services like Azure Functions, which can attach onto events coming in, game state changes coming out of the database, and use that to actually push down notifications using notification hubs back down to the end user. A few other areas we see a lot of usage is customer 360 scenarios. And a lot of this is basically people tend to, over time, what naturally happens at a lot of companies is they onboard more and more different data stores. And what you find is you have actual, like, let's say data and very many disparate sources. And what you want to do is you want to do some analytics and you want to bring all of this in. One way of doing this, doing so and making this easy is you use a schema agnostic store to actually be kind of one area where you kind of just land everything. And what you do is, it's actually pretty simple. Cosmos DB is a schema-agnostic store. It can support a high amount of data in it, but it's really optimized around high concurrency, low latency workloads. And in other words, it tends to be very, very frugal with the amount of compute resources per query. And so what you're going to do is you're going to use something like Spark on HD Insight to actually deploy a distributed compute layer on top of Cosmos DB to do your analytical queries. And this will actually bring the whole Spark ecosystem, like Spark ML or GraphX, to be able to do very, very heavy analytics using the Spark connector into all of this data landed in Cosmos DB. And really, the connector itself is quite nice too. What the connector does is, when you write something like a Spark SQL query, it'll actually look at the where clause in your Spark SQL query, take that where clause and bring it down to Cosmos DB and leverage the fact that Cosmos DB has automatic indexing and be able to actually very efficiently figure out what data needs to actually be pulled back up into Spark to build the data frames. And that way your Spark jobs are incredibly fast. They can be blazing fast. I'll kind of zip through this, but a few other interesting ones are around messaging. Messaging really is another use case where you tend to have lots of heavy write ingestion. If you want to do, let's say, a search experience over the messages, so that, like if you go back and sometimes you go, man, I had this conversation with my friend Magnus, and I don't remember exactly what that link he sent me was. So let me start searching for it. And so what you end up wanting to do is you can process these messages coming in. You can stem them, you can lex them, you can use something like a Lucene indexer, or you can use Azure Search for powering such an experience. And one pattern that we've seen is what people do is, well, they'll use the native partitioning offered by Cosmos DB and partitioned by user ID to absorb a high amount of messages coming in. What they'll do is they'll also do some manual partitioning where they'll create basically a collection or a container for each week, and this allows them to dial down the throughput on older collections and raise the throughput on whatever this week's collection is to handle all of those writes coming in. And this becomes a very, very easy way of actually managing a large amount of data over time, because what you find is, most people don't actually need to search for something that's really far back, let's say 2 years ago. And this is one technique you can use to actually kind of manage just both the cost of the overall system as well as how you actually wrangle the cost of just storing all of this data over time. The last area that we've seen a ton of usage is in content management systems. And for content management systems, a lot of the challenges are they are actually not in control of the schema themselves, right? Like if you're using something like .NET Nuke, rather than .NET Nuke saying, here's what the user-generated content will look like, the user will actually define what their user-generated content will look like. And so if you wanted to power something like a form builder, you basically want to expose a dynamic schema over to your users to define. And your end user does not want to actually go around and do a bunch of alter tables, create index. So what you want a system is capable of doing is take schema agnostic data, automatically index that, and then also globally distribute that in case you actually have a user base that spans around the globe. And so this is how .NET Nuke and a lot of various different SaaS vendors are now onboarding on a Cosmos DB. So this kind of gives you an idea of like what are some of the, at least the patterns I've observed over time in terms of how people are using this. Now let's take a look at just deeper at Cosmos DB itself. Like how do you actually build something off of this? For those of you who are new to Cosmos DB, I mean, the first thing to understand really is the resource model. These, at the end of the day, is the set of resources within Cosmos DB that you're actually going to interact with. And so at a very top level, the first thing you do is you provision a database account. A database account is basically the endpoint or a URI that you are actually going to connect to for your application to connect to the database. It's also going to have a key for controlling authorization. And the way you set this up in the Azure portal is actually really simple. Because this is a fully managed service, you just click on New, you go to Databases, go to Cosmos DB, and just fill in a few fields, including what that URI should be. what API you want to use. It is a multi-model database, so you can choose Graph API if you're trying to do graph traversal, or the document APIs if you want to do flexible schema workloads. You choose the subscription that you want to provision it on, a resource group, a starting region, and you're good. You click create, and now you have an endpoint up and running. Underneath the account, you want to think of the account as a logical resource. At this point, we actually haven't provisioned even our first data node. And so we're going to create a database. But even at a database level, that is still a logical entity. It's basically a logical collection of containers, as well as it'll have its own users and permissions that you can use for fine-grained access control on top of the containers and items. Containers are where things actually get interesting. We can project containers to various different data models based off of which API you have connected with. So if you're connecting to Cosmos DB using the Gremlin Graph API, a container will be a graph. Basically, all of the records underneath the items are going to be nodes and edges, whereas if you're connecting with, let's say, the MongoDB API or the Document DB API, you'll see a container as a collection. And of course, if you're using the tables API, what you'll see is a table. Items are, a few things to note about containers. The first thing you're going to do is you're going to just name it. But one of the neat things about containers is what we've done is we've actually brought provisioning, storage, and throughput down at a container level. And that way you can actually have hot containers, cold containers, and each of these containers are actually going to be elastically scalable. Basically, what you're going to do is you're going to define this thing called a partition key. A partition key is basically a hint on how we should distribute data coming in over a large number of machines. And I actually have some, we'll talk a little bit about this in just a second to give you kind of a real deep visual on how this actually behaves underneath the hood. And then, of course, items are going to be the records, the individual rows within the container itself. And there's going to be also a set of other resources, including stored procedures, triggers, and user-defined functions, which you can use to implement transactional business logic or extend the query language, and this thing called conflicts. Because we are a distributed system and we replicate your data across multiple regions around the world, conflicts are really there for doing things like automatic failover. If things are pending replication but don't actually reach the end destination during, let's say, an outage, what we do is we actually preserve that, and when the region comes back online, we actually guarantee the durability of everything you write to the database. So let's talk a little bit about given like that you now know kind of from a developer standpoint, what are all the resources and what do they look like? What does this actually look like underneath the hood? Underneath the hood, what we do is we actually, starting from a very, very high level, we start with planet Earth. We have a set of Azure regions. Today we have something like around 30 or so Azure regions, and these actually are going to be data centers. Within this data center, we set up these things called stamps. Think of these as like racks within that data center. And each of these racks are going to be its own fault domain. It's going to have its own network switch. It's going to have its own power supply. And what we do is we actually deploy a cluster over like 10 to 20 different fault domains. Each of these clusters is going to be basically a set of like hundreds of machines. Each of these machines will have a container which contains a replica. And then the replica is actually the fundamental building block for Cosmos DB and how we actually implement things like collections. When you create a container or you create a collection, what you're doing is you're basically acquiring a lease on 4 replicas underneath each partition set for each region. And this gives you basically a high amount of redundancy and be able to tolerate both failures across regions as well as within a region. Within a region, because we maintain 4 replicas for every partition set, if one copy goes down, what we'll do is we'll automatically bootstrap another. They're set up across different fault domains so that, you're resilient against things like a network switch going out. They're also split out across separate update domains, meaning your database never goes down either due to hardware failure or due to software update.
And this is Service Fabric technology?
So question is this based off of Service Fabric technology? Yes. Within a region, how we set up replication within a region is all using Service Fabric. And by the way, if you guys are interested in learning more about Service Fabric, I highly encourage you going to some of the talks at TechDays around this. There's another one here today, I hear. So now that we have the actual database replicas, I mean, a replica basically is going to be all of the software a database requires to run, right? It's going to be the query engine, the index. It's also going to control or have all of the data that you actually store. And it's going to have another aspect. Because this is built as a multi-tenant service, what we need to do is we need to implement resource governance to make sure that we give you performance isolation across tenants. You don't want noisy neighbor problems, right? But at the same time, you want low total cost of ownership. And the way we actually give you low total cost of ownership is these clusters are like many, many $1 million. So to make things low cost, what we do is we actually split this across a large number of tenants. And basically, there's two ways of building a cloud service. You either implement resource governance at a virtual machine level, or you can actually implement resource governance on the software stack itself. And what this allows you to do is guarantee performance isolation while packing even more tenants, and therefore lowering the cost of running the service and lowering the cost of what we actually charge you. And that's why Cosmos DB is actually going to be 3 times lower cost than any kind of VM-based solution. Now, the way we actually then resource govern is based off of this concept of request units. And request units you can think of as a logical abstraction over all of the physical resources it takes to perform a database request. This is going to be the CPU, the memory, the I/O. And the reason why we do this is we actually want to make it easy for you to actually do capacity planning. Initially, you think request units, so this is a new concept, this might be a little confusing. However, over time, what you come to actually realize is this is actually really quite convenient. Let me give you an example. Example is today I have a database application that serves 1,000 requests per second, and now I want to scale it to 10,000 requests per second. What do? If I had physical resources, do I get more RAM? Do I get more CPU? Do I get more I/O? How many gigabytes of RAMs is how many requests per second? I don't know. Maybe RAM is not even your bottleneck today, but once you get past, you buy some more CPU, now memory might become the bottleneck, right? And so to make this easy, what we do is we apply a machine learning model to all of the database operations coming in to actually understand what are the system resources operations typically take based off of if it's a query, what is the shape of the query, or if it's a create operation, what is the shape of the actual records being written. And this way we can also differentiate requests, like whether it's a create request versus a read request versus a delete request. Obviously, these things are going to be very different, right? Like for a create request or a write request coming in, we need to actually replicate this across all of our replicas. Whereas for a read request, depending on the consistency level, we might actually be able to just talk to a single replica and grab that data back out. But what we promise to you is predictability on how many RUs a request takes. So going back to that example of scaling from, let's say, 1,000 requests per second to 10,000 requests per second, if we know that these requests are, let's say, write operations, and these write operations will take 5 request units, that means that they're going to take 5 request units no matter how much data and how much throughput you actually throw at it. So initially, to handle 1,000 requests per second, if you think about it, 5 request unit per operation times 1,000 concurrent every second, that means I need to provision 5,000 request units to be able to handle this workload. Now tomorrow, if I want to scale to 10,000 requests per second, I just do the same math again. 10,000 times 5 is 50,000. And that way, just like that, in a minute, you can actually do all of the capacity forecasting in your head and know exactly how much you need to provision. Once you've provisioned this, this is basically like a token bag system, right? Every second, we're going to throw basically request units into a token. Every time you perform a request, we're taking these tokens out. If the token bag is empty, what the database will say is, hold on, token bag is empty, but if you retry in 1 second, you will have tokens back in this bag. And this is basically how we govern these resources. This is also how we give you predictable performance. We actually put SLAs around the latency you see for each of your requests, as well as SLAs on if you reserve resources, you will have that throughput. Like if you reserve enough resources for 10,000 requests per second, at any given moment, you can perform 10,000 requests, request units worth of requests in that second. So we guarantee these things by basically setting aside these resources ahead of time for you. And these are going to be, you can actually increase and decrease these instantaneously on demand, and they're metered hourly. And then we also have a set of things, background tasks running. So if you're not actually always using the peak, things like garbage collecting the log underneath to compact and make sure that we reduce your storage footprint, all of these kind of things will actually happen behind the scenes using leftover RUs. Now let's get into the fun things. I've talked a lot about, I think, kind of the context of, the Cosmos DB 101, but from a design aspect, if there's one thing you take away from this talk, this is actually the thing you want to pay attention to. How does partitioning work? So basically, when you provision a Cosmos DB container, the container can actually scale from no requests per second to millions of requests per second, from gigabytes to petabytes. Like, how do we actually do this? And the way we do this is you're actually going to tell us how you want to distribute your data and how you want to distribute your requests in the form of a partition key. So this is the number one design decision you'll need to do in order to make sure your application will work well on Cosmos DB. So let's use an example. Let's say we have like a multi-tenant application we want to design, and we're going to use user ID as the partition key because basically the amount of storage and the amount of throughput is going to grow with respect to the number of users. That is basically what will happen on the surface level. And the partition key is actually a logical abstraction. Behind the scenes, what we're going to do is we're going to hash that partition key. And that way, if you have something like user ID 1, 2, 3, 4, 5, it's incremental, you're not actually going to run into a hot partition issue just because everything is on the low end of the number spectrum. Instead, this hash is going to give you kind of a nice pseudo-random distribution of values. And what we're going to do is, on the physical side, is we're going to actually break up those values, the hashed values, into ranges. So out of the possible hashable values, let's say you have a system that requires 4 partitions to be able to handle all of the storage and throughput you need. What we'll do is we'll actually divide up the range into 4 even units, and those are going to map to the underlying partition. So that way what ends up happening is you're actually going to be co-locating a set of partition keys on the same physical partition. And by reducing the number of physical partitions, we're now reducing the overall cost of the cluster itself. Now, here's the interesting thing. Like, why do we actually take this hash range or consistent hashing based approach? Is what it does is it allows you to elastically grow on demand without having to worry about things like availability. So now let's say this partition, like maybe the one on the end, is filling up. What ends up happening is we can easily subdivide these partitions. And so what we'll do is we'll just cut that range in half. And that means half the partition keys, or roughly half the partition keys, might end up in one child partition. The other half will end up in another child partition. And now you have ample headroom to serve more requests and more storage. The net result of this is the database is going to elastically grow as your application grows. And what's really cool about this is we're not actually doing things like handing you tooling and telling you, hey, you figure out how to elastically scale your database. We actually do this as a service, as a built-in functionality of the service itself. And when things get that easy, it actually allows you to actually scale up and down on demand. When things are a bit more tricky, what ends up happening is you go, I can do it, but I don't want to, just because it's painful, right? So how do we actually choose a good partition key? You basically have 2 design goals that are going to stretch you into 2 different ways of thinking. The first design goal is you want to distribute the overall request volume and the storage volume across as many partition keys as possible. And what you want to do is avoid hot partitions. So an example of a bad partition key for a write-heavy scenario is current time. If you choose current time as your partition key, at any given time, all of your requests will have the exact same current time value. And that means all of the requests will actually get routed to one partition, leaving all of the other partitions idle. what you want to do is you want to avoid hot partitions. Naturally, what this does is it steers you towards choosing very, very fine-grained partition keys, like maybe even down to the actual document or records ID. However, on the other end of the spectrum is the read path, right? On the read path is when you run queries, if you can actually tell the SDK, like, hey, I've partitioned by, let's say, user ID, and I write a query that looks something like select star from this container where user ID equals Andrew, the SDK can actually be aware of, hey, I know where all the partitions are. I know how data is distributed. Andrew's on partition number 5. Let me just ask partition number 5. However, if you write a query where user ID is not in the where clause, then the SDK is going to go, well, I don't know which partition to ask, so let me, in parallel, ask all of them. Because this is parallelizable, the hit on latency is minimal. However, you are actually paying a throughput cost now in that you're using up throughput budget on every one of the underlying partitions. And so to make queries easier, typically what this does is it steers you towards choosing very coarse-grained partition keys. So now if you have one design goal that kind of steers you towards fine-grained partition keys, and the other is going to steer you towards coarse-grained partition keys, how are you actually going to think about this, right? Basically, what you want to do is you want to base this off of your workload. Try to ballpark the scale needs of your application in terms of size and throughput. And what that'll do is it'll actually tell you things like, you know what, I have a temperature gauge on just how many underlying partitions that might mean, and therefore how bad things like like a fan out would actually be. Now that I have an understanding of that, I'm going to take a look at the write path and the read path for my workload. How many reads per second? How many writes per second? And this way, I mean, if you have an occasional fan out, like maybe like this happens once a second, really, you shouldn't be concerned about this. What you should be doing is you want to optimize around Pareto principle. Operate and optimize your workload to 80% of your workload, and don't sacrifice performance. Don't sacrifice percent of the 80% for the 20%, right? Instead, optimize around the bulk of your workload. For the read path, what you want to do is you want to understand the top queries. If you go and look at, let's say, top 3 queries or top 5 queries, if you look at the where clause and look at all of the common things you're filtering off of, right away you'll have a very natural intuition on what is a good partition key for a read-heavy workload. If you look at the write path, the thing that you want to pay attention to is creates versus updates. And what you want to do is you want to minimize the cost of updates. And one of the anti-patterns I've seen in the past is people will like create these giant unbounded arrays within a single record and just be appending to this array. Over time, what you find is an array element is a very, very small portion of the overall record. You don't want to pay the cost of really expensive updates just to touch a small portion of it. And so these things are actually going to steer you on the object model, in which maybe that for that specific example, you break out the array elements into separate records. And that way you have very, very cheap, easy point inserts. But these are the things that you basically, if you walk through this steps, you'll really kind of gear your application or your design around Cosmos DB for success. Another general tip is a lot of people, I think, first time using the service, they're afraid of having too many partition keys. Don't be. This is a logical abstraction, right? The more partition keys you have, actually the more physical partitions we can spread that across, and that actually means more scalability for your application. So don't be afraid of having too many partition keys. In fact, having more is often a good thing. So this covers the partitioning side of Cosmos DB. The other side of distributed systems replication. And I think the easiest way to show you replication is to actually show you what the service looks like in the Azure portal. So let me jump over to the Azure portal. And here I have a set of database accounts I've already provisioned. And here in this, basically I'm going to go to the portal, the blade for one of my database accounts. And for this database account, I've already put it in 4 regions. Let's take a look at how replication and how setting up additional regions looks like. What you do is you click on the regions you want to add. Let's say I want to add this set of regions and really get a global presence. And maybe I want to remove this region, right? Literally what I do is I click what regions I want and I hit save. If you guys have had to set up geo-replication before on an on-premise workload, you know that life normally is not this easy. Setting up a new data center, setting up data center configuration, database configuration is a very nasty, long process. And so we've made this very, very easy. You literally click a button and say, I want this region. Once you have a set of regions chosen, you hit save, and what we'll do is we'll start replicating to all of these regions. Now I'm going to discard this, and I'm going to actually show you another thing. Let's take a look at how failover works. So now that you have multiple regions set up on a database account, what we can do is we can actually give you a high degree of resiliency such that, whoops, let me put these side by side, such that if one region fails, what we do is we can actually automatically fail over that traffic to another set of regions. And the way we're going to do this is we're going to define a global priority list after we turn on automatic failover. We can also do things, let me open up a code example. Not only can you define this at a global level, but you can also define this at an application level and override this. And where you're going to want to do this is, let's say I have a database in 3 regions. I also would want to have the application in each of these 3 different regions. But not all 3 applications instances in these 3 different regions should connect to one region, right? They actually want to connect to the database endpoint that's closest to it. And so what we do is we actually have the entire, all 3 regions hidden under a single endpoint. And that way, if you do have to do a failover, what ends up happening is you don't have to do an application redeployment. If a data center, let's say, experiences an outage, the application will actually gracefully fail over in priority based off of this ordered list. You can actually say, you know what, connect to this region as my first preference, and if this region were to go down, connect to this subsequent region, and then the next region thereafter, so that I don't have to do any kind of application redeployment. And so that way you have a very easy to maintain application that's highly resilient to things like regional outages. In addition to automatic failover, we also have the ability to do manual failovers. And this is useful for 2 things. Number one, it's useful in the context of just testing to make sure if you want to do your own business continuity drills. But number 2, what I think is very interesting about this is today what we do is we actually have this model where all the regions are active for reads, but we actually home all of the writes to a single region. This is actually going to be your mechanism also for changing the write region, and you can actually do this dynamically. You can even do, let's say, a follow the sun model where writes will follow the sun, and when it's daytime in the US, writes will go to the US, and when writes are when it's daytime in let's say here in Europe, then the write region should be somewhere in Europe. So this gives you the mechanism for building this. We also have programmatic access for doing this operation. And then as we now take a look at you know how to replicate data, one of the other things you want to be aware of is consistency, right? I kind of alluded to this a little bit earlier. And what happens if you write some data in one region and you want to observe in another region, right? Let's use an example, right? Let's have a 3-region deployment, and let's look at an individual partition set. In this partition set, each, I kind of mentioned this earlier, each partition is going to have 4 replicas per region. And what we're going to do is, whenever data is written, what we'll do is we'll do synchronous replication and get a quorum across a set of replicas in the right region. One of the replicas is going to be designated as a forwarder, and it's going to forward and asynchronously replicate to the other regions. And so the things you want to think about is, let's say I have a record whose value is 5 in each of these regions, and I want to update the value from 5 to 6. The first thing that you probably think about is Brewer's cap theorem, right? And cap theorem, basically, you're talking about given consistency, availability, and partition tolerance, what happens when there's a network partition? What happens when there's an outage? Let's say this region is experiencing, I don't know, a major hurricane that knocks out the local power grid. So if you have a reader that were to try to read from this region later on, like what should it see? Do you prioritize availability of the overall service and say it's okay if certain replicas lag behind? Or do you prioritize consistency? And because you can no longer maintain a consistent view of the world, do you actually bring the database temporarily offline? And this is kind of the concept of strong versus eventual consistency, right? Brewer's cap theorem basically says for a distributed data store, it's impossible to actually provide all three guarantees around consistency, availability, and partition tolerance. But the thing is that while most people, I think, understand Brewer's cap theorem, that only talks about the unhappy path, right? Like what happens when things go wrong. And really, the databases really, or data centers really don't go out that often. But there's still a very, very real trade-off with consistency with respect to performance with things like latency. When you update a value in the happy path, what happens is it takes time to propagate that data to other replicas. And so if you have observers in other regions asking what is the value, you actually need to be able to define some predictability on whether stale reads are okay or not. And so do you prioritize, let's say, very, very low latency? Let's say if you have a social media application, you're building something like Facebook. It's okay if I see my friend Magnus's comment, a second later, right? I don't need to have a fully, strongly consistent view of the world. What I want is I want the website to load really, really fast. It should be very, very snappy. Whereas if I'm sending, charging a payment from my friend Magnus now, stale reads might not be something I want, right? Like if I say, hey, this one of the orders he sent me hasn't been fulfilled yet, I process it for payment, and then I get a stale read saying, oh, it still hasn't been processed, so I charge it for payment again, he's going to be mad at me. So like at the end of the day, like what do you prioritize, right? Do you prioritize latency and throughput, basically performance, or do you prioritize consistency? And this is what the Pascal theorem really is all about. Given partition tolerance, or given a network partition, what is trade-off between availability and consistency? Else, what is trade-off between latency and consistency? And a lot of what a lot of databases do is they force you into these extremes. You either have like a high latency, strong consistency system, or you have an eventual consistency, low latency system. And I think this is where Cosmos DB is also what makes global distribution really shine. Is we actually have 5 well-defined consistency models so that the world's not so black and white. We actually have nice shades of gray so that depending on your scenario, you can actually choose what are the right performance versus predictability attributes that you want for your scenario. And so what we do is we offer this through actually just a click in the portal. We have strong consistency, bounded staleness, session, consistent prefix, and eventual. And basically, if you were to look at this on a spectrum from going strong to eventual, as you relax consistency, you're going to get lower latency, higher availability, and better read scalability. And so the guarantees that we actually provide are for the click stops in between. Things like bounded staleness basically is a guarantee of how eventual is eventual. And so you're defining actually a staleness window. Within this staleness window, by number of operations or about in terms of time. Outside of this staleness window, you have strong consistency. But within that staleness window, what we'll do is we'll relax consistency. The concept of session consistency is, what if we scoped consistency down to a session, right? Let's go back to the social media example. When I post a comment and I hit refresh, what I want is the page to be fast in that I don't want to actually slow my experience because of everyone else also posting comments. However, when I hit refresh, I better see my comment still there. Because if I write a comment on my friend's wall, on Magnus's wall, and I hit refresh and my comment disappears, what I'll do is I'll just write the comment again and press enter. And then Magnus is going to see that I posted the same thing twice, and he's going to be like, Andrew, what are you doing? Are you, you're a fool. So in order for me to not look stupid, what I want to do is I want to make sure that I am able to read my own rights, right? And so the session consistency is really, at the end of the day, what it boils down to is a read your own right guarantee. You have strong consistency within the scope of your session. We also can guarantee things like consistent prefix, meaning replication will always happen in the order of the writes are received. So imagine a messaging application. If I go, hey, let's go to dinner, what time is good? 7 p.m. Oh, I'm busy during then. How about 8 p.m.? Sounds good. If you actually replicate each of these messages just as they're received, a later message actually might find a better network path and reach to that end destination first. And so you might actually lose the order. If you now lose the order in context of this messaging application, things will get very confusing very fast. And so what we do is we can actually, in eventual consistency where you don't have any guarantees, we can strengthen this to consistent prefix and always replicate writes in the order that we receive them. Configuring this is very easy. For bounded staleness, you define the staleness window in terms of operations and time. For session consistency, what we do is we actually bind the consistency to this concept of a session token. By default, the client SDKs will cache the session tokens. However, if you want to actually, let's say you have a fleet of stateless applications and we want to preserve the session across all of these stateless apps, what you can do is you can actually pull out the session token every time you do a write request, pass it down to the user's cookie on the web app, and then pass this back up on the following read request to preserve that session across application instances. We can also relax consistency. So let's say you find that in common case you want bounded staleness, but for this one particular operation, you want it to return as fast as possible. You don't really care if this read is going to see a stale read or not. You can also override the consistency level in the request operations for every request. So I think I'm think now on time on the session, and to make sure we stick on time, for the other sessions. If you are interested in learning more about indexing and change feed, I'm actually happy to talk with you. Like I'll stand out here in the room and go over this. But this way, I mean, if you have questions, I mean, I'd also like to open up the room real quick to see, you know, if you, I'm here for you. If you have questions, I'm happy to answer. Anyone? Gotcha. Yes. Got it. So question for rest of the room in case you didn't hear is, what if I'm an existing table storage customer? I have many, many tables. What is my migration path into Cosmos DB, and how do I actually handle cost around this? So today, our tables API is in preview, and we actually have built out a roadmap in how we actually converge these two systems. You are right. What we are doing is over time, we actually are going to converge table storage into Cosmos DB. Step one is we're going to GA the tables API, but we made this available to you so that if you have, let's say, needs for secondary index, high throughput, low latency, you can actually start onboarding easily today. As we GA this, this will also mean existing tooling like AZ copy for moving data over becomes very, very friendly for you. But long term, what we want to actually do is make sure that you don't have to do manual migration. So over the next period of it's still a bit hazy, but about maybe a year or two, we're actually going to automatically migrate all of these workloads over onto Cosmos DB so that you don't actually have to do the work. We'll do the work. Now, one of the other things that we're working on, what you mentioned is costing and pricing. We actually are working on a basically what we call a storage optimized offer for Cosmos DB. Today, basically where Cosmos DB shines is high throughput to storage ratio, right? The cost for transaction is very, very small. Relative to table storage. And so if you have a hot workload, Cosmos DB actually gives you cost saving already. However, for cold workloads where you park a lot of data but not necessarily are constantly actually accessing that data, the pricing offer isn't quite optimized for this set of scenarios. And so before we do this automatic migration, our promise to you is we'll actually make sure that you are well taken care of. And what we're going to do is we'll be announcing over the next year or so a storage optimized offer so that you have basically all your bases covered, both for hot workloads as well as cold workloads. Cool. I'll take one more question. I think I saw a hand over here. So for consistent prefix, the way you solve this is we're a log append store. I I'll repeat the question. So how does consistent prefix consistency actually like work behind the scenes? Like how does it actually track these versions to avoid stale read? The way this works is we have a log append store, and each time you actually perform a write operation, that write operation is going to append to this log, and it's going to have a log sequence number. And what happens is our replicas, as they replicate to other replicas, they're always aware of what the LSN is caught up for all of the other replicas. So if we replicate the log in LSN order, and let's say this one is aware that I'm at, let's say, read 500, I'm at LSN equal 500, and over here, this one's still at, let's say, 490. It knows that I need to replicate 490 to 500. Now, as this one kind of moves ahead in time, now what it's saying is it's not strong consistency, but for a consistent prefix, all of the replication will happen in order, meaning you won't have change in order, you won't have gaps in time. And so if this is caught up to, let's say, LSM 500, it guarantees that all of the operations that happen before it are going to be there. You won't have gaps in time, right? So if you write operations 1, 2, 3, what we guarantee is if you see 2, you will see 1. If you see 3, you'll see 2 and 1, and those will also, the order will be preserved. This is at least for how consistent prefix is implemented. And we also play some tricks with LSN for some of the other consistency models. Cool. So I'm going to be respectful of our other speakers' time. Thank you very much for attending my session. I am asked to tell you, please evaluate my session. If you loved it, evaluate it. If you hated me, maybe don't evaluate it. That way Magnus won't be mad at me. But yeah, thank you very much. And I'll be here outside if you want to chat.